Okay, section 4.5, excuse me, this is integration techniques. As I said in the last video, this is our first advanced technique. This is kind of the base point, and this is substitution, or as I and many others call it, this is U substitution. Substitution. And so our one and only objective is to evaluate integrals using substitution. So we have three basic rules for integration. The first is the power rule. The integral of u to the r du equals u to the r plus 1 over r plus 1 plus c. We have the exponential integration rule. The integral of e to the u du equals e to the u plus c. And we have the natural log rule, which is the integral of du over u equals ln absolute value of u plus c. So these are the three that we talked about at the start of chapter 4 and we've been using. Now notice I didn't do f of x and dx, I used u and du. And that's because what u substitution is all about, and why it's called u substitution, is you start thinking of u as a function. So u could be your f of x. Your du then needs to be f prime of x dx. So the next couple examples that we have here are designed to highlight that. So in part A here, we have y equals f of x equals x cubed. And we want to find dy. Well, we know that from our differential section in chapter 3, dy is f prime of x dx. That's the differential. And this equals 3x squared dx. Now notice, if you were to integrate, you would integrate 3x squared dx, and we know that that's going to be x cubed plus c. Here's the interesting part, and where u substitution, what the whole point of it relies on, is this is equivalent to integrating dy. Because this is really a 1 dy, it's never just dy on its own. The antiderivative of 1 is the variable that you're integrating with respect to. This is y plus c. Well, y is x cubed. So that's why we call this substitution. So for u substitution, in part B here, we have u equals capital F of x equals x to the 2/3. So du would equal 2/3 x to the negative 1/3 dx. So if you were to integrate, you would need this whole thing to get back to x to the 2/3. In part C, du, since u is ln of x, du, which is g prime of x dx, is 1 over x dx. In part D, we're back to y's. dy is f prime of x dx, which is 2x e to the x squared dx. So when you are using substitution, what we're essentially saying is that we could integrate dy, we could integrate f prime of x dx, but we don't always have this perfectly the way it is. And that's what we have substitution for. So the next couple examples are a way to outline substitution. So let's start with this one, the integral of 3x squared times x cubed plus 1 to the 10th. So we have two basic functions here, 3x squared and x cubed plus 1. The trick with substitution is we don't have a product rule for integration. So what we're implying is that one of these is the derivative of the other. So we have to pick u that makes this work. Well, the u that makes this work, since it's x cubed and x squared, is if we make u x cubed plus 1. Then du would be 3x squared dx. And look, we have 3x squared dx. Multiplication is commutative, so we can put these two together. So if I substitute, hence the term of the technique, the name of the technique is substitution. This is the integral of u to the 10th du. The du sucks up the 3x squared and the dx into 1 du. We have u to the 10th. And now we can integrate this using the power rule of integration, u to the 11th over 11 plus c. And then swap back to x's. U is x cubed plus 1, quantity to the 11th over 11 plus c. And so it allows us to integrate more complicated functions. So similarly, this guy over here, we have two functions, 2x and 1 plus x squared. And you're always trying to identify the u, and then you get your du. So you're not picking du, you pick the u. So which of these is the derivative of the other? Well, we have an x squared. The derivative of x squared is 2x. So x squared plus 1, or 1 plus x squared. Same but different. Du is then 2x dx, our definition of differentials. And so we can substitute 2x dx becomes du. 1 plus x squared equals u. And now this is nothing more than the ln of u in absolute value plus c. Switching back to x's, this is ln x squared plus 1 plus c. And that becomes our final answer. So the whole point of u substitution or of substitution is to take a complicated integral and make it look like one of these three. U to the r, e to the u, du over u. Notice in both of these examples, u to the r, u to the 10th, du over u. So if you're trying to figure out if you've done it right, if you've picked u correctly, your integral will look like one of these three. Exactly these three. So let's look at a couple more examples. And then I have some practice ones for you as well. So in this we have 2x, and we have 1 plus x squared squared. So I'm going to choose u to be 1 plus x squared again. Du is then 2x dx. I have the 2x and the dx, so this becomes the integral of du over u squared, which is the integral of u to the negative 2 du. Notice we're right back to that last sheet. Those general forms, we are u to the r du. That's what we have. So this antiderivative is negative u to the negative 1 plus c. Or switching back to x's, this is negative 1 over 1 plus x squared plus c. Okay, moving on to the next one. This one's a little bit trickier. We have ln 3x and we have x. So those are the functions. So what you have to ask yourself is, which of these is the derivative of the other? Well, you'll never get to ln 3x by taking derivatives. So we're going to have to set u equal to ln 3x. And that's just because we don't know any derivative of a function whose derivative, we don't know any function whose derivative is ln. So if u is ln, then du is going to be 3x over 3x or 1, or 3 over 3x or 1 over x dx. Well, we do have that. We have 1 over x dx. So this is really the integral of ln 3x times 1 over x dx, or the integral of u du. Again, we have our u to the r is 1. So the antiderivative now is u squared over 2 plus c. Switch back to our x's. This is ln 3x, quantity squared, over 2 plus c. So the next 4 are practice problems. I recommend that you pause the video and try these out yourself and see how you do. Start by picking your u. Make sure your du is there. If you pick a u and your du is not in the integral, you've picked the wrong function, or perhaps you just haven't picked enough of the function. So I'm going to go through these now. If you haven't done them, please pause the video and try them out yourself first. So in this first one, we have the integral of dx over x plus 3. So since I don't have any other functions, the only function I have is x plus 3. And du of that would be 1 times dx. Well, I do have 1 times dx. So this becomes the integral of du over u. And I can look at my 3 options. It should be u to the r du, du over u, or e to the u du. I have du over u, so I know I've done this right. So this is ln absolute value of u plus c. Switching back to x's, this is ln of absolute value of x plus 3 plus c. That's our derivative. So on the next one, it's a little bit trickier. We have x e to the x squared dx. Now, a lot of people's first reaction is to choose u equals e to the x squared. And then our du would be 2x e to the x squared. But we don't have 2x e to the x squared. So there is a way to do this. But we don't have this piece. So instead, let's pick u equal to just x squared, and then du equals 2x dx. Now, the point of u substitution, and we're going to talk about that on this example because it makes the most sense, is to pick the function for u whose derivative is already there or mostly there. And so what I mean by that is the derivative 2x e to the x squared we don't have. So if we're going to be integrating u du, we need to have du and we need to have u. We don't have the e to the x squared because it gets soaked up into the u. So over here though, while we don't have 2x dx, if I divide by 2 and get rid of this, we do have du over 2 because we have x dx. Remember, it's commutative, so I can move these two things around. So my integral is really the integral of e to the u times du over 2, and we can always pull our constants out using our constant multiple rule for integration, e to the u du. And now I know I've done it right because I have a form that we're used to. So this becomes 1/2 e to the u, the antiderivative of e to the u, plus c. Switching back to x's, we have 1/2 e to the x squared plus c. And that would be our final answer. Coming down here now, we have a definite integral. The integral from 0 to 1 of 5x square root of x squared plus 3. So this is here to show that we don't necessarily need to have an indefinite integral when we use substitution. It's a technique to find an antiderivative. So we have two functions here, 5x, x squared plus 3, and I'm ignoring the square root because I know that the square root, its derivative is another square root on the bottom, and I don't have any fraction here. So my u is going to be x squared plus 3. My du then is x squared, or I'm sorry, is 2x dx. Now I don't have this, so I'm going to divide by the 2 again like we did up here. And I'm going to rewrite this as 5 times the integral of 0 to 1 x to the square root x squared plus 3 dx. So now when I make the substitution, the 5's not going to get in the way. So x dx becomes du, and I have the square root of u. So this becomes 5 times the integral from 0 to 1 of the square root of u times du over 2. Pull the 1/2 outside to go with the 5, 0 to 1, square root of u du. And we know that the antiderivative is then going to be u to the 3/2 times 2/3, since the power here is 1/2. And this gets evaluated from 0 to 1. And when we evaluate this from 0 to 1, we get approximately in our calculators 4.673. All right, so once you plug in 1 and 0, which is really just plug in 1, then you can get your answer. But I did make an error here on purpose. So this is the right answer. I forgot to change our limits of integration. So these limits are x's. So I need my u to equal 0 plus 3, which equals 3, and u to equal 1 plus 3, which equals 4. So this should be 4, and this should be 3. So this should be 4, and this should be 3. 4 and 3, 4 and 3. And the reason for that is we transition to use, oh, not here yet, 1 and 0 still there. We transition to use from this step to this step, so we need to transition all of our x's to use as well. And so you do that by just plugging in your x values in your limits of integration into your u equation here. So I apologize for messing that up. Now, if you do what I did and you forgot and you left it 1 zeros all the way down, you could also just switch this back to x's. Instead of u, plug in x squared plus 3. So on our last one here, x over x plus 2. This one is a more challenging u substitution. So they give us the domains so that we know we're not dividing by 0. So if u equals x plus 2, then du is just dx. Now there's a problem here, is we have another choice. U could be x, and then du is just dx. So what we have to do is, number one, always pick the larger thing when your du's and dx's match here and here. So we're not going to pick this one. And what we're going to do is we're going to take this and say x is now u minus 2. So if we do this substitution with all 3 here, let me just split that. This substitution with all 3 of these pieces gives us the integral of u minus 2 over u du. And then this becomes the integral of 1 minus 2u to the negative 1 du. Since x is strictly greater than negative 2, x plus 2 is not 0, which means u minus 2 is not 0. Which means that we can divide this out and not worry about any issues. And then the antiderivative here is u minus 2 ln times the absolute value of u, not times, 2 ln of the absolute value of u plus c, or switching back to x's, x plus 2 minus ln of x plus 2, ran out of space, plus c. And that's our final answer there. So this is a special and more sophisticated U substitution, and that's when you can think of your two functions as equal in weight. Right? This is a linear and a linear. So neither of them are derivatives of each other. Okay, so if we flip the page here, this on the back is some strategies. This is a reference page for you for U substitution. So these are kind of the things you want to be thinking about as you're looking at substitution rules. So number one, you want to determine what rule of integration, basic rule of integration you're using, the power rule, the exponential rule, or the natural log rule. Then calculate your du. Then you're going to look at your integrand, the thing that you're integrating, and maybe you need to insert the constants like we did. That was the dividing by 2 for the du's. So something like this would be step 3 here, where we insert the constants to make it work. Perform the anti-differentiation. Reverse your substitution, go back to x's. If there are bounds, use them to evaluate the integral after the substitution has been reversed. Or 5b, which is what we did, is do not reverse the substitutions if the limits of integration have been converted from the original variables to values of u. Use those new converted variables. And then always check your answer by differentiation. You should take your derivative and you should get your answer. Obviously not true for definite integrals. If you have a definite integral, then you don't want to. So what I want to do is come back to this problem now and talk about this a little bit more in depth. So we had the integral, 5 times the integral from 0 to 1 of x square root of x squared plus 3 dx. And I said this can be written by substituting in for u equals x squared plus 3. Then du is 2x dx. And we said this becomes 5/2 square root of u du. And then plugging 0 into u here gave us 3, and plugging 1 into u gave us 4. And then we evaluated like we always did without switching back to u's. So what I want to talk about, this is 5b. That would be 5b's rule. Let's look at how we would do this with 5a. So when I initially wrote the problem, I had 5/2 integral of 0 to 1 u to the 1/2 du. And I didn't change my limits of integration. And then we integrated and we had 5/2 u to the 3/2 times 2/3 from 0 to 1. So if you don't change your limits of integration, at this point, like I did, you could go back and switch them. Or you can write this as 5, simplifying a little bit here, 5/2 times 2/3 is 5/3. And then it's x squared plus 3 to the 3/2 evaluated from 0 to 1. Now up here, we said that this was 5/2 u to the 3/2 times 2/3 evaluated from 3 to 4. So I just want to compare what these look like. So this looks like 5/2 times 4 to the 3/2 times 2/3 minus 5/2 times 3 to the 3/2 times 2/3. So that's what this one looks like. This one here is 5/3 times 1 plus 3 to the 3/2 minus 5/3 times 0 plus 3 to the 3/2. Well, 5/2 times 2/3 is 5/3. 1 plus 3 is 4. 5/2 times 2/3 is still 5/3, and 0 plus 3 is 3. So these two things are the same. So you're allowed to do this in any way you choose. If you want to switch back to x's and not worry about your limits of integration, you can. If you want to just leave it as u's, you can also do that. But know that both of these will get you the same answer. So that is substitution. I gave you an example of how to do definite integrals. We did the complicated version of substitution where you have to do a kind of a triple substitution. Everything else is very straightforward. You have your strategy list here. You can refer back to this. It'll be a good resource. But this is the end of 4.5.